Good evening and welcome to our final presentation of the day, using Delta-rs and Delta-kernel-rs to serve CDC feeds. I will now pass the presentation over to your presenters, Steve and Osama.
Hello, everyone. Thank you for coming out. As our presenter had just said earlier, this is using Delta-rs and Delta-kernel to serve CDC feeds. And so some paperwork to get out of the way, just forward-looking statements, as well as please go and fill out your surveys. I love statistics, so if you do, I will definitely see anything that is put there. So please go and do that if you get a chance. We appreciate it. And so let's start off by going through what we're going to do for an agenda real quick. So Osama is going to start us off by talking a little bit about what CDF is, like what its application is, and the data space of things. He's also going to talk a little bit about Delta kernel. If you haven't gone to any other talks this week about kernel, we'll talk a little bit about what that is, why you should use it, why it's cool, things of that nature. And then the challenges that we had when we were implementing CDF for Delta specifically. There is some nuance to that we'll get into. And then I will take back over and talk about Delta-rs and its CDF implementation and how that is leveraged through kernel. The problems that we had with the initial implementation, how the kernel fixes those problems, and then how we actually did the integration. And then finally, we'll have kind of a combined demo and questions going. At the end, I'll just show a little bit of using some Sparkless Delta-rs to do some analyzation of some CDC feeds. And yeah, and I think we'll get started. So without further ado, I am Steve. I guess that was obvious. And so I'm a senior RSA here, so I work in the prof serves. I've been a core contributor of Delta-rs for, I think it's been 2 years now, something like that. I'm the implementer of a bunch of stuff in it, check constraints, CDC, Unity catalog integration, things of that nature. I've been around Rust for about 8-ish years, something like that. Time flies when you're having fun, I guess. And then here you go.
Hey folks, my name is Osama, and I am a software engineer at Databricks. I work on Delta-kernel-rs. So this is like sort of the core of this Delta protocol implementation that we'll be talking about today. I am the author of the CDF and in-commit timestamp implementations in kernel. And finally, I am a systems and Rust enjoyer. So if you want to talk databases, come on up and talk to me after this talk. All right, so I want to introduce to you, what is change data feed and why do you want to use this thing? So change data feed represents all of the changes that have happened at each commit on your table. So you can take a look at, at version 1, I added a column, or added a row. At version 2, I added another one. Version 3, I deleted one and added a new one. And so you can think of this as sort of the deltas that have happened at each version of your table. And if you take the integral of that, if you bring it all together, you have the final state of your table. So what does this get you? Well, one application is this idea of incremental materialized views. So let's say I want to maintain this idea of the total price of all of my products. And this is a bit of a dummy example, but it gets the point across. And suppose I want to keep track of that for every day. I want to see what's the total price at all times. If you had to run this query repeatedly, that becomes really expensive. Right? So how can we make this more incremental? How can we pay less on our compute using CDF? Well, so instead, let's keep track of at each version, what changed. Over here, I added 2 new items. Okay, well, I only have to increase the value of my total revenue by just that amount instead of doing a full table scan and reading the whole table and figuring out all of my total revenue. Right? So this becomes a much cheaper query compared to the full table scan. Another one is ETL. Let's say you're bringing in a bunch of data, maybe these JSON blobs, and it's unstructured, it's not cleaned. And maybe you want to have a cleaned up version, your golden table. your ETL pipeline can consume that change data feed, see what are all the changes that have come into this rough JSON blob table, and refine it. Only the things that have been updated. You don't want to repeatedly update and refine the things that have come in previously. Now comes in the Delta ecosystem, right? Okay, so this Delta table has the ability to showcase these change data feeds, but for every connector that you have in your ecosystem, in your data platform, they have to re-implement that over and over and over again. So this is where kernel comes in, right? You want to do your CDC, and you want to consume it from all these different places. The idea is for kernel to bring this all together to one spot, so that not only can you do change data feed, but you can also do type widening and look at identity columns and so on. The way that I like to pitch kernel is a small trade offer, right? As long as an engine or a connector is able to give us the ability to read JSON and read Parquet, we give them the full Delta protocol. And so with that, any engine that is able to read Parquet or JSON is able to read these change data feeds. That becomes pretty powerful, right? You can now use DuckDB. You can connect to it through .NET, or you can connect to it through Flink or Trino, and so on. Now, implementing CDF in Delta kernel was a little bit tricky, right? At a high level, you need to get a log segment. You need to go through that log. You need to figure out the paths of the data files that have been added and removed. We also have to consider deletion vectors, and that's tricky. Okay, so we need to resolve those. And finally, we read the data files and tell you what has changed in your data so that you can go ahead and keep that incremental materialized view. So you can do that ETL pipeline. So let's take a look at an example. I create my Delta table. First commit, I added some data. Okay. Well, let's say I want to remove some data. Okay. Well, we added a deletion vector. Logically, what we did was we removed the old data and added it back again with a deletion vector. That's how it looks like in the Delta log. And let's say I update it again, I remove another row. This is what it looks like, right? Logically, we remove that old path, remove that old data, and DV. We add a new one, right? So this is sort of what we're given from the Delta protocol, and this is what we need to wrangle. Now let's take another look at a different example, right? Let's say I have some more data coming in. And I did an update. And logically, inside the Delta table, what happened was we updated, but physically what's going on is we removed an old data file and added a new one. So we have to resolve that and sort of figure out what has been changed in each update. And so here's an example of us resolving these deletion vectors and figuring out what's been added, what's been removed at each version, right? And showing you some of the complicated deletion vector logic. You know, if it was previously removed and then afterwards it was not removed, then it has been added, right? So we have to do all of this tricky sort of logic in Delta kernel in order to surface that to all the connectors in the ecosystem. Let's take a look at this example over here where we have a CDC file. And once again, it's Delta log operations that the connector ecosystem would have to go through. They would have to go and figure out, oh, I need to go read the CDC file and figure out what's the pre-image and what's the post-image. This is stuff that we've implemented in Delta kernel Rust. But that's not all. There's also timestamps. Now, you're able to do time travel over your table. You're also able to do CDC over timestamps in your table. I want what have been the changes between Monday and Tuesday. Kernel has to go figure that out so that you don't have to in your ecosystem. Let's say I want to find the version at 190. We're able to use file modification timestamps and just go straight away. We found it. There's trickier cases with more advanced Delta features in in-commit timestamps, where the timestamp is inside the commit. You have to do a read. So it's a little bit trickier to find. Let's say I want to find the first version that happens after timestamp 220. Well, we know it happens after the in-commit timestamp, so we have to go read it. How do we do this? We go do a binary search. Okay? Let's start at the middle of our range, 300. Are we there yet? I don't know. Let's go to the left. 200. That's too low. 225. Perfect spot. Now, why am I showing you this? This is, again, complexity in the protocol that we've abstracted away from connectors so that the entire ecosystem can do it and not just Spark. So Delta kernel, in short, implements all of that just once for the entire ecosystem. And I'll pass it off to Steve to tell us about Delta-rs.
All right. My mic works, right? Or am I not yelling into it enough? Okay, so let's then talk about Delta-rs, which is the Rust implementation of the Delta protocol. And so this is a project that happened, that's been around a little bit longer than the kernel, but it's, as I said, an open source implementation there. And so we implement the majority of table operations in Delta today. If you use Delta in Databricks, you probably will notice there are a couple things that you can't do in Delta-rs that you can do in Databricks. But we get the majority of stuff. If you want to merge, insert, update, things of that nature, then you're good. But if you want some extra features, like say deletion vectors or uniform or liquid clustering, those are not available right now in Delta-rs. It doesn't mean that we won't get there eventually, but they're not there today. By the way, if you want to contribute, by all means, we'd love to have additional people come and help us with that. But yeah, we've been working on this for about 5 years now. And so the majority of the contributions from this are actually non-Databricks contributors as well. Well, Robert Pack was not always a Databricks employee when he contributed, but I believe I was the only Databricks contributor for quite some time. But the majority of this is owned and driven forward by non-Databricks people. So, you know, it really is like an open source, like, you know, out there in the wild. So anyone can contribute, come and talk to us about it. You know, we'd love to have extra people coming and help. And so let's look at a brief example. I know this is not really a talk so much about code, but let's just give you a brief example of what reading CDF from a Delta table looks like. So this is an example taken just right from the documentation. You can copy pasta this into a file and compile it and run it. Granted, you have something at that's I went 1, 2 forward. Granted, you have a table actually at that location there where my first arrow is pointing. You know, you will be able to just read a Delta table through that. From that, we then create a data fusion session and associate data fusion with that table. And we then load CDF. CDF uses a common builder pattern for it. So you specify, in this case, I just specified an end version. And so in this case, it would use the default version of 0 to start. So this would be a read from version 0 to version 4 of said table. And then you just, you know, build it. And so after that, there's a little bit of housekeeping for partitioning in order to kind of distribute this. And then we just collect it and print it out. And so this is what, like 10-ish lines of code. If I can't count right, please don't hold that against me too much. But this is a very low amount of code in order to get like a CDF read. And just to be clear here, there's no Spark involved in any of this. There's no JVM here, there's nothing. Like if you were to build this and give someone else the executable, granted they also have a table at said location, this would just work. No JVM, nothing else, they don't even need Rust installed. It's a statically linked binary that you can just pass around to anyone. And so now that we've looked a little bit about that, let's talk about the initial implementation of CDF in Delta-rs. As the author of it, I also know where all the skeletons are buried for that implementation. And pretty much every mistake I made along the way in doing this. And so the first thing and the most obvious thing was there's no deletion vector support. So if you had a table that had deletion vectors enabled on it, it's just not going to work. And as Osama had mentioned a little bit here, that's mostly because we don't have deletion vector support anywhere in Delta-rs right now. It's something that we'll eventually get from kernel integration. But it's very difficult to actually figure it out. Osama spent a lot of time doing it for kernel, but at the time I was just lazy, I guess is the best way. I don't actually remember why I didn't implement it at the time, but it would have forced me to basically implement it everywhere in kernel, in Delta-rs, and we didn't have it at the time. So I wanted to get CDF in. I didn't want to implement deletion vectors in literally everywhere, and so we just sided with no deletion vector support for that. And surprisingly, that actually worked out because we eventually wanted to get it through kernel anyway. And so in an opposite case, if we had implemented it, we would have had to rip out all of that logic in order to let kernel do the deletion vector stuff, and we would have had a bunch of code that we would have eventually just gotten rid of anyway. Another thing is that if you tried, so there was a time where if you go and you install an old version of Delta-rs and you try to read a table with CDF and deletion vectors enabled, you'll get something back. Whether it's correct, I don't know. That was a bug that we eventually fixed in a subsequent version where if you have deletion vectors enabled, since we don't support it, you just can't read the table anymore. So it's no longer possible to get entirely incorrect who knows what it is, but for a time that was also possible. Additionally, timestamp support, both in kernel as well as in Delta-rs, has been I guess inconsistent at best is maybe the right way to describe it. Delta-kernel always had file modifications, as well as like the JVM implementation also uses file modification times for doing some of these operations sometimes. Eventually, another feature in Delta came along called in-commit timestamps, which remediated the issue of needing to look at the file modification time. Turns out not every file system actually gives you good file mod times, so relying on this didn't always work. Correct me if I'm wrong there.
Yeah, another problem that we tried to solve with in-commit timestamps was that it was not monotonic. And so you could go up and up and up and then back 5 days and then forward 10 days. It was the Wild West in the old file modification timestamp. So in-commit timestamp ensured we only go forward in time.
Yeah. And you know, if you've ever written timestamp, time zone code in literally any language, it's always a pain. I always get it wrong personally, so you know, this was especially difficult. And in the initial implementation, I just used file modification, so there was no ICT awareness at all. So, like Osama had said, if you had some wacky delta log that went forward, backwards, you know, up, down, left, right, whatever, then sometimes that would be confusing because while my example only showed off reading versions, you could also use timestamp ranges to also read versions. So if the commit messages themselves were all messed up, then timestamp reading was also kind of messed up too. And so as I had mentioned, I know I always get ahead of my slides before, but it would lead to basically inconsistencies in the reads based on the timestamp. And so what we did was, Osama and I have been talking about this for many months, but we eventually led to replacing the read path of Delta-rs with the kernel's version of it. And so this actually was really easy. I actually just deleted a lot of code and replaced it with the kernel version of it. We're currently in the process of doing a lot of kernelization in Delta-rs right now, so you know, there are a lot of moving parts in here that could change and you know, go in different directions. Whoops, I was not supposed to show that just yet. But you know, there's still some testing that we have to do for this, but for the most part, it kind of came out to basically like a net 1,000 lines of code like removed. And so now, when it breaks, go to Osama.
It's my problem now.
Don't come to me. Well, you can still come to me, but I'll probably just send you to Osama. And so just as a little PR message too, we haven't merged this quite yet, so that number may change. Don't hold me to that one. But so the end result of this integration was that like now you get deletion vector support. You can read it with a table with deletion vectors enabled. You will get correct, consistent results. You can, if you're using an older version, you now get correct results. If you're using a newer version, you now can actually read CDF. You also can have whatever wacky timestamp, time zone versioning like weirdness, and the timestamps will resolve correctly because now we have in-commit timestamp, but if that's not available, it falls back to file modification time, like what it was previously. So results among that, again, consistent, correct, everything like that. And I don't have to manage like a large swath of code. I think I've only done actually 2 or 3 bug fix PRs and releases on the CDC path. So while I normally don't write very good code, this has actually exceeded my expectations for amount of weird mistakes I've made throughout the time writing it. And so now it's less of a maintenance obligation for Delta-rs. We have enough code we have to rip out in kernelization. This was one of the easier ones to kind of get through. And so, that's not to say that there isn't future stuff that we could do that would, help us make this better. And this is both work on the kernel side as well as on Delta-rs's side of things as well. Probably the first one would be more data fusion integration. Delta-rs uses data fusion all over the place to do a lot of things with merging, inserting, like essentially anything that does like a SQL-oriented thing, check constraints. They all require an actual execution engine, which data fusion provides for us. And so CDC currently from kernel actually returns these things called record batches, which if you've gone to any of the 3,000 talks about Arrow across the week, you'll probably hear about record batches somewhere in there. They're the general abstraction for kind of a blob of data in Arrow. Sorry, any Arrow PMCs in the crowd that was totally wrong, sorry. But essentially, it currently returns record batches out of it. And preferably, we would like it to return just files to read, because that would allow us to wire it more into data fusion to get better like metadata, statistics, things of that nature. Basically build like a more SQL-oriented like logical plan instead of what we do right now, which is basically just take the record batches, put them in a data source execution in data fusion, and hand it back to you. So the ability for like the data fusion planner and optimizer to do stuff, reorder things, like look at it, is essentially none right now. But that's something that we can definitely do down the line. And this would allow us to do things like I had said, so we could separate like just scanning metadata, just figuring out what we have to read versus actually going and reading it. Currently, kernel reads both things. It does both sides of it. And normally what we would do for kernel is we would plug in, we would let the engine actually do the reading of the data path. The kernel would just tell you what to read. And so, but currently we're kind of breaking our own contract a little bit here. Just look the other way for now. And so yeah, but again, like this is something that we're going to have to, there's a lot of open discussion about where and what needs to go where for this. So it's kind of an open and evolving topic. Again, if you'd like to contribute to any of these things, you're more than welcome to join the conversation. We're always happy to have more people in it. All right, so let's hope that I can do this considering I'm kind of navigating from a window that I can't see on my end. And so, so I've just taken the time to create a very small, not very good Lakehouse app that is deployed on Databricks. And so you can see my URL up there, Databricks apps. This runs on AWS. And this just reads a very small CDC table that sits in Databricks. It's a managed Unity catalog table. And so I have the versions that you can actually read from, or that. And so since I don't specify a version here for my neat little app, it actually gives me a rundown of all of the subsequent versions and what has actually happened in them. So we can see, like, for instance, in commit version 10, I inserted 3 rows, so on and so forth. Updates happened in version 4. Osama talked a little bit about the update pre-image, update post-image type thing. And you can see I've done a bunch of deletes and a couple inserts across the line. And so again, this is a Unity catalog managed table. This Delta-rs actually gets Unity catalog vended credentials from this, so this doesn't have AWS keys signed up to it. It doesn't have any idea where this table is. It actually goes to the Unity catalog API to go and grab these credentials and go and know where to read this from. So this has no credentials essentially given to it or associated with it. It gets all that stuff through Unity catalog. So I know the talk's not about Unity catalog APIs and credential vending and stuff, but it does make doing a lot of this stuff a lot easier as well. And so if we go up here, and thank God this has been easier than I thought, and say like we'll change it to 4, and then we'll go to say 8, why not? And so we can then reread, and we will get just the things that happened in 4 and 8. So just to show that this is not a pre-canned kind of thing here. But if we scroll down a little bit, I have also taken the time to do a little bit of, this will generate some very mild code for you that you could potentially run in Databricks with some light modifications here. And this actually looks at the schema of the table that Delta-rs gets, and will build, say, your DB SQL statement or your Python code to dynamically build this. So this table actually has a schema of name, age, salary, birthday. I just made it up. And so it's all dynamic based around that. And so if you plug in a different table, it will obviously build a different merge statement based on what the schema is here. And so with a little, like I said, with a little bit of modification, you can copy pasta this into either Notebook or DB SQL console and run it. And it'll probably break the first time. You'll probably have to massage it a little bit. I can't guarantee this works 100% of the time, but all the basic building blocks are there. The only reason I didn't actually do the write back with Delta-rs, which totally could happen here, is because Unity catalog vended credentials for writes hadn't come out yet. And so when that is available, you'll be able to do all of this through Delta-rs. Maybe in a Lakehouse app, if you can somehow do it in 6 gigs of memory. That's still kind of a small amount of memory for anything. But yeah, so I just wanted to give you an example of something that you could do that uses all this. There's no Spark involved in any of this. And yeah, I think, do we have any other questions or anything? If not, I think we're good. This will also be on GitHub later. I have to open up the repo. It's private right now. And five minutes to spare, not bad.
Yeah, we have 5 minutes. Feel free to stick around and ask questions if you so desire.
Thank you very much.
Thank you.
I have to also say, do your surveys again. Please, if you want. I won't be offended if you don't.